Hello everyone, my name is Ahmed Sarfu, and I'm a senior at Seven Lakes High School. I'm here today to talk to you about modular arithmetic. Modular arithmetic is a topic in mathematics that is used in number theory, and it can be used to solve many seemingly complicated problems. Okay, so let's begin by learning some basic modulus. Okay, so a simple example of modulus can be seen on a clock. So let's say we go to school at 8 in the morning, and we come back from school around 3. Okay, so we have 7 hours elapsed, but we don't say 15 o'clock after 7 hours after 8 o'clock. We call it 3 o'clock. But why is this? Well, that's what happens when you take a modulus of 12. So when we're saying 8 plus 7 equals 3 o'clock, we're actually saying 8 plus 7 mod 12 is congruent to 3 mod 12. Okay, so basically when we're doing modulus, we're comparing numbers based on the remainder when divided by the base right here. So for example, we could say that 4 mod 12 is congruent to 16 mod 12, which is congruent to 28 mod 12. Okay, so let's begin with addition and subtraction of mods. Okay, so we saw earlier that 4 plus 8, for example, mod 3 is the same as saying 4 mod 3 plus 8 mod 3, which is the same as 1 mod 3 plus 2 mod 3, which is equal to, congruent to 3 mod 3, which is congruent to 0 mod 3. But if we go back to the original problem, we see 4 plus 3 can just be written as 12. 12 mod 3, and since 12 is a multiple of 3, we already know that it's going to be 0. So now we know that we can add and subtract in mods. Okay, so in the regular integers, we know that multiplication is the same as adding repeatedly. So we can use that logic to say, for example, 6 times 8 mod 7. Okay, so we know 6 is already in mod 7, times 8 mod 7. Okay, so we have 6 mod 7 times 8 mod 7, which is equal to 6 mod 7 times 1 mod 7, which is equal to 6 mod 7 at the end. Okay, so we know 6 times 8 is 48, and 48 when divided by 7 gives us a remainder of 6, so we checked our answer. And now we know that multiplication is, we can use multiplication in mods. Now, there's also a different approach to this problem, which I find is more clever. So we know, again, that 6 times 8 mod 7, correct? Okay, so instead of saying 6 is already in mod 7, we can rewrite 6 as negative 1 mod 7, and we can write 8 as 1 mod 7. Okay, and so we know 1 times negative 1 is negative 1, and so this equals negative 1 mod 7, and that's 6 mod 7. So we're done. And so using negative and mods can often save us a lot of work. So we know that multiplication is repeated addition, and exponentiation is repeated multiplication. So we can apply our logic for multiplication to prove exponentiation in mod. So for example, let's take 16 to the 15th power mod 5. Okay, so what do we know about this? We know that 16 is congruent to 1 mod 5. Okay, so then we can say that 1 to the 15th mod 5, which is obviously just 1 mod 5. So now we know that we can add, subtract, multiply, and do exponents in mods. So now we can move on to some example problems. Okay, let's take a look at this problem. What is the sum of the units digit and the 10 digit of 7 to the 643rd power? Okay, so this seems like a pretty big number to us. So how are we going to calculate the whole thing? Well, if we use mods, we don't even have to calculate the whole thing. So we're looking for the 10th digit and the units digit, correct? So if we're looking for the 10th and units digit, we can take a mod of 100, and we'll get numbers from 0 through 99, which is what we're looking for. So let's do this. Let's take 7 to the first, mod 100. And we know that this is just 7. 7 squared, mod 100, is congruent to 49. 7 cubed, mod 100. Oh, you know 7 cubed is 343. So it should be congruent to 43. And 7 to the fourth, mod 100. Well, 43 times 7 is equal to 101. And so we just have we end up with 1 right there. And then we go to 7 to the fifth, mod 5, mod 100. And we return to 7. So what we see is we have 7, 49, 43, 1, and then we have 7 again. So now from seeing this, we know that the pattern should be cyclic because every single time we multiply by 7 in mod 7, we'll end up with another number in the cycle. So we have 643. And from this pattern here, it's clear that anything that has mod 1 is congruent to 1 mod 4 will have 7 at the end. Anything that is 2 mod 4 will have 49 at the end. Anything that's 3 mod 4 will have 43 at the end. Anything that is 4 mod 4 will have 1 at the end. And so on. So we have 643. 643 is clearly 3 mod 4. So we're going to have a 43 at the end. So 4 plus 3 is equal to 7. So 7 is going to be our answer. Okay, so here's the next question. What is the remainder when 5 to the 263rd is divided by 7? Okay, so this seems similar to the problem we had earlier, except instead of taking a mod of 100, we would be taking a mod of 7. Okay, so we have 5 to the 263. Now, earlier we took a mod of 100, and luckily our cycle only had 4, but the cycle can often have anywhere from 4 up to like very large numbers. It could have maybe 10 numbers in the cycle. And if we're doing exponents of 5, we're going to get to pretty big numbers there. So maybe there's a faster way to do this. Well, if you think back to the multiplication trick, we know that 5 can be rewritten as negative 2 to the 263rd. And, well, 2 is a pretty easy power to work with. So let's work with this instead. Okay, so we have negative 2 to the first, same process before. Okay, and so that's congruent to negative 2 mod 7. Okay, then we get 4, and then we get negative 8, we get 16, we get negative 32, and we get 64. Okay, 64 would be negative 2 to the 8th power. And we also know that 7 times 9 is 63. So 64 is congruent to 1 mod 7. So in this case, our cycle is to the first power, second power, third power, fourth power, fifth power, sixth power. So our cycle is 6. And so basically we're doing the same thing again, except we're trying to figure out what this is in mod 6. So 263 is going to be, so we have 240, so we have 23 left, and 23 is going to be 5 mod 6, okay? So we're looking for which of these elements is 5 mod 6. So we end up with negative 32 is 5 mod 6. So we had to find negative 32 mod 7. Okay, and so this is going to be the same as negative 4 mod 7, which is equal to 3 mod 7. So we know that when 5 to the 263 is divided by 7, we'll end up with a remainder of 3. Okay, so this is our last problem. Okay, so let's see. Find a positive integer that is a multiple of 3, not a multiple of 9, and a perfect square. Okay, so we know that any integer, if it's a multiple of 9, it can be expressed as 9x for some x. And so if it's a multiple of 3, it can be expressed as 9x plus 3, or 9x plus 6. Okay, so if we take, alright, so we know it's a sum of n squared equals these two numbers. Okay, so we know if we take a mod of 9, that n squared mod 9 is congruent to 3 or 6. Okay, and we also know that every single integer of the set of integers can be expressed as 0, 1, 2, 3, 4, 5, 6, 7, or 8 mod 9. Okay, so what we have to do is we take each of these and square them and see if we can end up with a 3 or a 6 when it's squared in mod 9. So 0 squared mod 9 is 0, 1 squared mod 9 is 1, 2 squared mod 9 is 4, 3 squared mod 9 is 0, 4 squared mod 9 is 7, 5 squared mod 9 is 7, 6 squared mod 9 is 0, 7 squared mod 9 is 4, and 8 squared mod 9 is 1. Okay, so from this list of n squared and mod 9, we can clearly see that there's no 3 or 6. So that means that there exist no integers that when squared in mod 9 will yield a 3 or a 6 in mod 9. So that means that there's no solutions to this question. That's it for today. Thank you for watching, and I hope to see you on my next video. Have a nice day.